This is a video about energy and energy considerations when we are dealing with these magnetic forces. The big thing we need is this. We know that our force, magnetic, is going to be charge times velocity crossed with our magnetic field. And this cross product, really, that's just what's causing the perpendicular response, which means that we know that our force is necessarily going to be perpendicular to our velocity, and our force is necessarily going to be perpendicular to our magnetic field, even if the velocity and the magnetic field aren't perpendicular to each other. Now, this one, that's great. That's not what we're worried about for this particular video. What we're looking at is this force being perpendicular to velocity. If I have a charged particle like this, and it's moving in this direction, if I have any particle and it's moving in that direction, I can apply a force, and that force can go any number of different ways. Now, what I need to remember for this is that the sum of forces is going to be a mass times an acceleration. So when I think of a force, I can think of an acceleration. If I have a velocity pointing in this direction, and I have a force that points parallel to it, an acceleration that points parallel to it, then I will be speeding up. If I have an acceleration that points opposed to it, then I am slowing down. But what happens when I have an acceleration that is perpendicular? When I have an acceleration that's perpendicular, I'm not speeding up and I'm not slowing down, which means I must be going at a constant speed. Now, constant speed doesn't really feel like an acceleration sort of thing, but we can accelerate by changing the velocity vector, and we can change the velocity vector by changing either the magnitude or the direction, or both. We're not changing the magnitude because we're not speeding up and we're not slowing down, so we are going at a constant speed and changing the direction of our motion. There is a time that we have already done this way back in the distant past of Physics 1, and it looked like this. If we were moving in this direction and we had an acceleration vector that was perpendicular to our velocity vector, we knew we were going to turn. So now we are moving this direction. But our acceleration vector is again perpendicular, so we turn some more. And what we end up with, ultimately, is a circular path. So a magnetic force can very nicely lead to a centripetal acceleration. But here's the thing. I've got my velocity and I can't affect the magnitude of my velocity, right? So if I want to look at something like kinetic energy, which is a half mv squared, this v squared doesn't care about a direction, right? It's, for those who play this game, it's a velocity vector dotted with itself. But the other way to look at this is to say it is the magnitude of a velocity times the magnitude of a velocity. We don't care about the direction. If we can't change the magnitude of the velocity, we can't change the kinetic energy. If we can't change the kinetic energy, then we must be going through some kind of a uniform circular motion, because we can't change the energy and we're turning, which means we will be able to use formulas that we've used before, like centripetal acceleration is equal to v squared over r, and that lets us put things together. We can now say our magnetic force magnitude might be a qvb perpendicular, and that's equal to a mass times an acceleration. The acceleration is going to be v squared over r. And now we have a way of finding a radius of curvature of our path. This is a radius of curvature. We are going to be able to use that for a few different applications, for actually many applications, but only a few that we're going to use in this course. But those are issues for a future video.